Hello, my people. Hope we're doing well. Um, for the review for the test that is coming up, I figured the best way to do it, besides giving you those review packets, is to run through as many of these cumulative questions as we can. And so you get much more comfortable with them than you otherwise would be. And so I'm going to try to do maybe one cumulative question per video, since they're plenty long enough to fill up a video. Let's go ahead and get started on this one. I don't know how long ago I put this on a test, but this is a question that I gave to some of my kiddos some years ago. Given the functions below, answer the following questions. And we're given f of x is equal to negative x plus 5, so linear. And then a transformation on the reciprocal function, which is g of x is equal to 4 over x. Now, those only, obviously 4 over x is obviously going to be in the third quadrant as well. But those overlap in the first quadrant like this, okay? This one right here, the one that curves, is obviously your g of x is equal to 4 over x. This right here is our f of x is equal to negative x plus 5. Okay. I need to find the area between the curves. Now, finding the area between the curves, we first need to find the points of intersection because they're going to give us our limits of integration. So let's go ahead and set f of x equal to g of x. This basically just winds up being a really simple rational equation, and we're going to get negative x squared plus 5x minus 4 is equal to 0. Or we can go ahead and multiply through by a negative if you're more comfortable with that, because numerical factors don't impact zeros. And then we can factor this one into x minus 1 and x minus 4, and therefore we realize that our limits of integration are going to be 1 and 4. Well, that's nice. Okay, so let's go ahead and move along and actually perform some of the things that we're being asked to do. Okay. Now, actually, let's go ahead and kind of try to double it up like that so that we can still keep the question in view. I need to find the area between the curves. Now I know that my limits of integration are 1 and 4, and if you want to see what that looks like on the graph, at 1 it's right here, and at 4 it's right here. Now those happen to be, because of the reciprocal function, 4 over 4 is 1, so this is going to be 4, 1, and this of course is going to be 1, 4. Okay? But since I'm integrating with respect to x, for right now all I'm really interested in is 1 to 4. Okay? Now, if I'm finding the area between the curves, I need to go from 1 to 4. We know that the linear is above the reciprocal for the area for the region that's been defined. Okay, so the linear is higher; it is more positive than the curve. Okay, and therefore it is going to go first, and we're going to call it 4x to the negative 1 because in that form it's just easier to integrate. And then we're going to subtract our f of x, and we need to be very careful to make sure and distribute that negative. And so we're going to get 4x to the negative 1 plus x minus 5 dx. Now, when we're dealing with this one, obviously if you're going to add 1 to the exponent, it's going to be x to the 0. And if you're thinking, gosh, that's a problem, you need to remember that 1 over x integrates into natural log x. And so basically what happens here is we have 4 natural log x. Now, I would usually put the absolute value bars around the x here in natural log x. But seeing as our limits of integration are both positive, it winds up being a little bit unnecessary. So I'm going to evaluate this from 1 to 4. Okay. And so I'm going to get 4 natural log 4 plus 1/2 times 16 minus 5 times 4. That is, big F of 4. Then I need to 4 natural log 1 plus 1/2 times 1 squared minus 5 times 1. And simplifying this ought to be, really easy. Remember, natural log 1 is 0, okay? This is 4 natural log 4. You could change the form by means of properties of logarithms, but, who cares? Because you're just going to wind up putting it into the calculator anyway. This winds up being 1/2 minus 5, so negative 4.5 or negative 9/2, but I'm subtracting that negative 9/2, so I then, of course, want to add the 9/2. Now, let's go ahead. Let's use our calculator. So we have 4 natural log 4 plus 8 minus 20 plus 4.5, and we see the fact that we're going to get negative 1.955. And the reason is because from the very get-go I flipped it, right? I said that the linear was on top, and for some odd reason I put the reciprocal first. And the thing is that when you get a negative area, you're obviously going to want to go back and check what you did wrong. The first thing you need to check is did you put the more negative function first? I did, because despite the fact that I put the graph up there and explained to you why the linear went first, I was a bonehead and didn't do it that way. If you wind up with a negative, the second thing you need to check is, did you accidentally flip your limits of integration when you went to the evaluation phase? Like, despite the fact that you have 1 to 4, do you have the 4 natural log 1 plus 1/2 times 1 minus 5 times 1 over here on the left instead of the right? Because obviously flipping a difference will obviously give you a negative as well. But basically what that tells us is we went back up, we checked, I recognized the fact that I put the more negative function first in the integrand difference, and that's the reason for it. Now, let's go ahead and let's move on to part B. Okay. Now, part B says, find the volume of revolution around the x-axis for the region bounded by both graphs. So if we're going to be revolving it around the x-axis, basically we're going to have to determine our big R and our small r. Okay, so we're going to be spinning it around here. Just like the area, we need to determine which one is more positive, which one is farther away from the axis, and of course it's the same region, so it's still the linear. Okay, so when we do this, what happens is we need to identify our big R. And our big R is the linear. So our big R squared is, 5 minus x squared, which, is the same thing as x minus 5 squared, so whatever. Our small r is 4 over x. Our small r squared is 16 over x squared, or 16x to the minus 2. Now remember, when we're dealing with the Washer method for volumes of revolution, the formula, and I hate formulas, but remember that it's pi, remember the pi, very important, then your limits of integration, and you need to do r squared minus r squared, and then your differential, okay? So in this case, that's going to be, my limits are 1 to 4. My big R was 5 minus x squared. My small r squared is 16x to the minus 2 dx. Okay? Now, let's go ahead and let's simplify this, and you wind up getting x squared minus 10x plus 25 minus 16x to the minus 2 dx. Now, I'm going to go ahead and I'm not going to do this one by hand, largely because I want to save a little bit of time, okay? Let's go ahead and plop the linear into y1. Let's go ahead and put the transformation on the reciprocal function into y2. And when you go back to your home screen, the only problem with doing it with y1 and y2 is you need to remember to square them, okay? And you also need to remember to put the pi out in front. So pi times the integral from 1 to 4 of y1 squared minus y2 squared dx, okay? And we get a volume of approximately 28.274, units cubed, right? Okay. Now, more than anything else, I want to see this. That's where the lion's share of the points come from, because basically setting up the integral is conceptually the most significant thing to do, okay? Actually doing the busy work and the computation, that's annoying sometimes, and you can make careless errors, but I'm more interested in, do you understand the concepts? Well, let's go ahead and move on to part C. Now, given the function h of x is equal to f of x minus g of x, so we've already dealt with the difference between f and g. Now, this problem is redefining or defining h as that difference, okay? Let's go ahead and take a look at this. I've gone ahead and printed it out. This negative x plus 5 minus 4 over x, this whole thing is that reciprocal function, okay? And I've boxed in the part that we sort of zoomed in on, because what it was asking for is find the volume of revolution around the x-axis for the region bounded by h and the x-axis, okay? So what I'm going to do is I'm going to spin this around the x-axis, okay? Okay. Now, and then it's going to ask me to compare that value with the one, oh no, this one isn't asking me to figure out that. Okay, so let's go ahead and find that volume of revolution. Now notice from the picture that this is going to be a little bit different than the last one, because our area is actually flush up against the axis of revolution. This is disk method. This is not going to be washer, okay? And we can even go into our calculator and sort of, make this work for us. We can go ahead and, if it's going to be f minus g, we can actually program y3 to be y1 minus y2, okay? Let's go back to the home screen. Now, given the function h of x is equal to f of x minus g of x, find the volume of revolution around the x-axis. Well, revolution is going to be pi. It's still going to go 1 to 4, because where these two are equal, their difference is going to be equal to 0. And if you're kind of like, what? Notice that the points of intersection are here at 1 and 4. And, you could actually work that out algebraically by taking the difference function, turning it back into a single rational expression, factoring it and looking for the zeros. We won't do that right now. But f minus g winds up being f minus g. Well, since it's flush up against the axis, this is my only radius that I'm squaring. So instead of the difference of squares, you're going to have the square of a difference. So it's not going to be the same value, okay? So let's go ahead and we'll go ahead and put our obligatory pi right here. Let's go ahead and go for the integration from 1 to 4. It's going to be y3 because that already contains the difference that I'm interested in, and we're going to integrate it with respect to x. And this winds up being 4.864 units cubed. Okay? Okay, well that was kind of fun. Let's go ahead and move on to D. Find the volume of the solid created by the region bounded by both curves, meaning we're back to the original one, okay, not H. We're back to here, back to the pink region that is bounded by both curves. Find the volume of the solid created by the region bounded by both curves and square cross-sections perpendicular to the x-axis. Now remember, when we're dealing with square cross-sections, we don't have a constant out in front. Still going from 1 to 4, and we need basically our s of x, right? Our expression for the side of those cross-sections, and that's just going to be f minus g. Okay, so what I'm going to do is I'm going to square that because it's a square, multiply it by dx, and what I'm going to get basically is I'm going to get what I just got up here divided by pi, okay? Okay, so delete, delete. And what I have here is 1.548 units cubed. And the only way it would be different is if it were a different cross-sectional shape, is instead of a 1 out here, for equilateral triangles it would be √3/4. For semicircles it'd be pi over 8. And if you don't remember that, I'll just refer you to the videos where I basically derived all of those for you to explain why those different constants simply sit out in front of exactly the same integral. Now let's go ahead and let's finish this up. Let's look at E. Now find the volume of the solid created by the region bounded by H and the x-axis and square cross-sections perpendicular to the x-axis. Well, here's the thing. The difference, our s of x, is also our h of x. So E is going to be identical to D, okay? And that may seem weird, the fact that, let's go ahead and look at both shapes. It may seem weird that the cross-sections, square cross-sections run from 1 to 4 along this is going to be exactly the same volume as the one for here, but remember this is just zoomed in, okay? But here's the thing. At any x, the height of h is equal to the difference in height of f and g from the original function, right? And so whether you square it as the difference in order to find s of x, or whether you're squaring it actually as h of x is immaterial. It winds up being exactly the same thing. So we wind up getting, you know, since s of x is simply h of x for this particular scenario, we get exactly the same integral and therefore the same answer. Okay? This is only the first of several that I'm going to do for you. I hope that these are helpful. As always, shoot me a message if you have any questions, and I will look forward to hearing from you. Bye.